I am Dr. Hemalatha, Department of Mathematics, aided. So, in this session we are going to learn about solving ordinary differential equations of first order but higher degree, that is non-linear degrees, there is more than one. So, a general non-linear first order differential equation is given in this manner, where the n stands for the power of p is the dy by dx, the differential term, and here we have x as the independent variable and y depending on x, a dependent variable. Now, when we have to solve a type of such equations, we mean a solution. What will be the solution of such equation? It has to be free from differential terms, that is a relation between x and y, which can be put up as f of x comma y equals 0. Geometrically, this f of x comma y equals 0 represents a family of curves. Now, when we talk about solution, we have three types of solution, which is general solution, particular solution and singular solution. What is a general solution is, if you have one independent variable, you have one arbitrary constant. When we say arbitrary constant, according to the problematic cases or the situation, we can have a different constant values as per the need. So, we always try to get a general solution. When we give some values for the arbitrary constant based on the conditions we arise in experimental or practical purposes, we arrive at a particular solution. And we are not holding any more arbitrary constants and we need a solution, we call it as singular solution, which is again an envelope of the family of curves, that is, you put all the solution in one head, which forms the envelope of the solution, called the singular solution of the problem. So, in this content we are going to discuss about the general solution of one particular type of ordinary differential equation. When we talk about the solution, again we have talked about three terms. One is x, one is y, the third is p. So, x is the dependent variable, independent variable, and y is the dependent variable, whereas p is the differential term. Now, how to solve this kind of problems is by four types, because every problem of such kind cannot be put under one single solutional method. So, we put under four categories. The first is, some problems we can solve it for y, some for y, and some for p, and some for x, and some for in a special case of Clairaut's form, if it is so. So, now we will discuss the method for solving the first type, that is solvable for p case. Suppose I am given a general problem in p, where I can put factorizing the linear equation in p as putting it as linear factors. Then I can use the first type, that is what I meant solvable for p case. First type is applied when I can put the given general equation, this kind of general equation is given and I can put into linear factors, then I can go ahead with this particular type of problems. So, suppose in this problem I have generally taken n factors, n linear factors. What is the second step is, I need to equate, because it is in a product form, I can equate this to each of this to 0, apply a variable separable technique of integration and get a function in x, y, and along with an arbitrary constant which is applicable for basic integration. Now, solving all these n factors, we will be getting n solutions, but n arbitrary constant, whereas we have only single independent variable. So, I make all the arbitrary constant to be under a single C category and combine all in a product form, which is actually our general solution. Now, to learn more about this, we will look into one illustrative exam part. So the very first discussion is we have an equation, solve this equation, differential equation, p square minus 9p plus 18 equals 0. Now when you talk about factorizing, we know all factorizing techniques in algebra. So we apply a factorizing technique and put it into two linear factors, p minus 6 product p minus 3 equals 0. So as discussed in the working rule, we equate this to each of this to 0. We have p minus 6 equals 0, convert p as the original dy by dx format and variable separable, you get dy equals 6 dx. Integration, a simple integration leads to integral dy gives you y, 6 integral dx gives you 6x plus an ordered arbitrary constant. Now again go to the second factor, do the same way of integration and you get the second solution. Combine the two and make a general solution, which is the actual solution of the problem in a general case. That is our first illustration. Coming to the second one, we have a problem, solve p square equal x cube. The difference is here we don't have a y explicit term, but we do have a y term because p stands for dy by dx, so y is hidden. So here also we can bring out a solution f of x, y, c. When you talk about this particular solution, there is no need to factorize much because there is only one single p term and the right hand side is the power of x term. Just make a square root on both sides, we can get the dy term and integrate further. When you talk about the integration in the left hand side, it is y plus c. No wonder why I have added a plus c in the left hand side. Integration constant can be made either in the left or in the right accordingly. So right hand side we have an integration x to the power 3 by 2. So apply the integration formula, x power n dx is x power n plus 1 by n plus 1. I will be getting this. Now remove the radicals by making a squaring on both sides. I will be talking about 25y plus c whole square equal 4x power 5, which is the general solution of the second problem. Okay, I hope you have learned the first two, which were very simple discussions. We will move on further learning with the third problem, where third problem is given as a cubic equation in P. You can always solve any power of P if it is factorizable by this method. Though this is a cubic equation, we observe that there is a P term in every first and second and third term. We can just remove a P and make it a quadratic with a P common term. So this again can be factorized. You get a P product xp minus 2y product yp plus x in our usual way and equate each one of it to 0. When you talk about the integration step in the second factor, it is integral dy by 2y. So 1 by 2 integral dy by y is nothing but log y. So we have given a log y equal log x plus log c2. Log c2 is inserted because that logarithm can be removed by taking exponential on both sides. And apply some basic logarithmic rules, you get the solution as y equals c2 x power 2. So likewise you go ahead with the third one, same by yp plus x integration, changing p as dy by dx and doing the variable separable scheme. You get y dy plus x dx. Here the integration is integral y dy is y power 2 by 2, the same x power n plus 1 by n plus 1 integration formula. Now change all the arbitrary, because you have three factors, change all the arbitrary constants to symbol c and now you get the product form, which is the general solution. Now coming to one last discussion for today's learning, we have a special case of discussion where you talk about another form of P. If you observe the question, the last fourth one is solve dy by dx minus dx by dy. So there is something to be done over there. It is very simple, just make it a P minus 1 by P, 1 over P. because it is not dy by dx, it is dx by dy equal x by y minus y by x is the same as given in the question. Now again go for the factorization, make it a quadratic equation and bring out the linear factors. Equating to 0 each one of the factors, we get your solution for the 2 and combine to get your general solution. So these are some problems which can be worked out and further learning can be made for solving particular case of solvable for P problems. Other content will be shared in the next part. Thank you.